In this video, we're going to discuss the Gibbs energy of mixing for ideal gases. So what I want to do is consider a system here where we have two different gases. So let's say we have gas A and gas B. Initially, they're in this container that has some sort of divider that is not permeable to the gas molecule. So the gases are fully secluded in their own parts of this container, not allowed to mix with one another, right? What we're going to do here is pull up this divider. You can just imagine it's some type of slider. You just pull this divider up in the container, and that allows the gases to now mix together, right? So initially, they're going to be in their own contained volume of this container at their own temperature and pressure. Right. And then when they're allowed to mix, now they become a gas mixture. Now they have access to a greater volume, and the pressure of each gas is going to be denoted by Dalton's law, where each one is exerting its own partial pressure in that volume container. Right. So the idea here is that we want to be able to define a Gibbs energy associated with the process of mixing gases together, right? So the big picture of what we want to do here is we want to define a delta G for mixing, right? And in order to do that, we're going to have to define a Gibbs energy after the mixing occurs and subtract that from the Gibbs energy before the mixing occurs, right? So your standard, final minus initial, we want to be able to characterize the Gibbs energy after the mixing has taken place and subtract that from the Gibbs energy before the mixing has taken place. So keep this visual picture in your head as we go through the mathematics here. Okay, so we know we have a differential for the Gibbs energy, right? So we know that dG is going to be equal to VdP minus SDT, right? So in this case, I've specifically written temperature consistently here. This is going to be an isothermal mixing, right? So this mixing occurs in such a fashion to where the temperature does not change, right? So the temperature T is going to be consistent throughout the entire process. So that means that for our differential, right, our dT term goes to 0 since it is isothermal. So that means that dG is just going to be equal to V dP. And since we have an ideal gas, we know what the expression for this volume is going to be. It's going to be the volume for an ideal gas, given our state function, right? So we have nRT over P dP. Right, that gives us our change in Gibbs energy, right? We know what the state function is going to be, so we know how the volume changes with respect to pressure. So we're just plugging that in. Now, obviously, if we want the Gibbs energy here, we're going to have to integrate on both sides, right? So if we integrate on the left-hand side, right, we're going to have some final Gibbs energy. We'll call it G2, some initial Gibbs energy, G1, right? Integrating dG. Now on the right-hand side, right, we know that the temperature is held constant. The number of moles is constant with respect to the total number of moles of the gas, right? So we know that that guy's constant. Obviously, the gas constant is constant. So we can pull all those guys out of the integral. nRT comes out. So we're just integrating from some initial pressure P1 to a final pressure P2 of 1 over P dP, right? So on the left-hand side, you just end up with G2 minus G1, simple there. And the right-hand side, we've seen this integral before, nRT ln P2 over P1. Right, so if we want to get a final Gibbs energy, right, it's just going to be the initial Gibbs energy plus nRT ln P2 over P1, right? So this is going to be how your Gibbs energy changes for an ideal gas, right? So you're going to have some initial Gibbs energy G1, and you add on this change with respect to pressure And that gives you your final Gibbs energy. Now, we can actually re-express this guy in terms of the chemical potential if we divide both sides by N, right? Divide by the number of moles. If we do that for both sides, right? So let's do that here. If on both sides we divide by N, so we'll have G2 over N is equal to G1 over N. And then when you divide by N with that last term, right, you just those cancel out. So we're just left with RT ln P2 over P1, right? So G2 over N is just going to be the chemical potential. And G1 over N is also the chemical potential, right? So the chemical potential, the initial and the final chemical potential respectively, right? Plus RT ln P2 over P1. All right, so this is just your general expression for being able to solve for the chemical potential, the change in the chemical potential for an ideal gas. Now, something that's going to be very useful for us here is that we can use the standard pressure as a reference point. So we can use standard pressure, which is 1 bar, as a reference, right? Since you have all of these different thermodynamic variables that are tabulated at standard pressures, this gives us a good reference point for calculating the free energy change at any point, or the chemical potential change at any point. So basically what we're going to do here is re-express this with standard pressure being our reference point, right? So instead of saying mu1, I'm going to say mu naught, right? That not just being for the standard standard chemical potential. So the chemical potential is taken at standard pressure, right? And so P1 would just be our standard pressure. So I'm going to use P naught here again for the standard pressure. Okay, so that means that we can re-express this expression, right, for our mu is just going to be equal to mu naught plus RT ln P over P naught, right? So this is just using our standard pressure to get a standard chemical potential, and using that to just have a general expression for the chemical potential, using the standard pressure as a reference. So now we can use this expression to define chemical potentials for each of our components here in the gas mixture, right? So we can define a chemical potential for A, right? Well, that's just going to be mu A naught plus RT ln P over P naught. And the same thing for the second component, right? We'll have mu B is just equal to mu B naught plus RT ln P over P naught, right? So we've defined a chemical potential for each one of our substances, right? Keep in mind that this is, irrespective of any mixing, right? We've just calculated, we've just given a general expression for each of our chemical potentials for each component in our mixture, right? So before these guys are mixed together, we can write a general expression for the mixing, right, that we're going to call G before. So sticking with this notation up top, I'm going to call this the G sub before, right? We know that we have a general expression for the total chemical potential for a mixture, right? We talked about this in one of the previous videos, where we can write this as mu A Na plus mu B NB. Well, now we have expressions for our chemical potentials. So let's plug those guys in. Right, so we'll have mu A naught plus RT ln P over P naught. Right, and that's multiplied by Na plus our chemical potential for B, mu B naught plus RT ln P over P naught. And that's going to be times the number of moles of B. Okay, so this gives us a general chemical potential, right? Or the general expression for what happens before the mixture, right? So this is our G before, right? Now, if we want to get a free energy for after the mixing occurs, keep in mind that after the mixing occurs, we're dealing with different pressures, right? So we can still use these general expressions, right? The only difference here is that we're going to have to deal with the partial pressures PA and PB, right? Those pressures change from just being total pressures of these divided volumes to now being partial pressures with respect to the total volume of the mixture, right? So we can define a G after mixing in the same way, right? We know that mu A times Na plus mu B times Mb is going to give us the total Gibbs energy after the mixing occurs, right? So here again, we have mu A naught plus RT ln, right? For A, now we're going to have the partial pressure of A, right, over P naught, plus similar expression for B, right, PB over P naught, right, MB. Okay, so here we have our expressions for the Gibbs free energy before mixing and after mixing, right? So we have everything we need here to thermodynamically quantify the Gibbs energy change for the mixing process, right? So I'm going to do this. I'm going to start this on a new slide. But basically what we're going to do here is take our expression for G before and G after and just subtract them, right? And we're going to get some cancellation and get a simpler, cleaner expression. So keep in mind, the goal here is to quantify the delta G of mixing, right? We're taking G after, subtracting it from G before, right? Our delta G before, our Gibbs free energy before and after mixing, right? So after, we had Na, mu A naught, plus RT ln, right? So we had those partial pressures, right? Plus NB, mu A naught, plus RT ln PB, P naught, right? Now we have G before, the terms from G before, right? So we have minus Na, mu A naught plus RT ln P over P naught minus NB mu naught B plus RT ln P over P naught. Okay, so we have this term, right? This expression for our delta G of mixing, right? This is our total delta G of mixing, right? And we can actually simplify this guy quite a bit. What you'll notice here, even without doing the expansion, right? You'll notice that these terms that depend on the general chemical potential, right? The standard chemical potential, those are all going to cancel out, right? This guy is going to cancel with this guy, right? Because you're just going to end up with a Na times mu A naught term minus Na times mu A naught. Same thing here. Nb mu B naught, right? That guy's going to cancel out with this one, right? So we end up with all of those standard chemical potential terms canceling out on us, right? So then when we bring all of this stuff down, we just end up with NA RT ln PA over P naught plus NB RT ln PB over P naught minus NA RT ln P over P naught minus NB RT ln P over P naught. Okay, so now we're left with this expression, right? So what we can do is actually take advantage of a rule of natural logs, right? So we know that for any general natural log, right, if we have the natural log of A over B, we know that that can be rewritten as ln A minus ln B, right? So I'm going to make use of this rule of natural log here in order to break all of these guys up, right? So for this first one, right, we'll have NART ln PA minus ln P naught plus NBRT ln PB minus ln P naught minus NART ln P minus ln P naught minus NB RT ln P minus ln P naught. Okay, so now from this point, right, here again, just like we did in this step, right, all of these terms that depended on the standard chemical potential all canceled out. Same thing is happening here with these terms that depend on the standard pressure, right? So this one would cancel out with this one, right? Because they're both being multiplied by NBRT, right? But with opposite sign. And then same thing here, right? This guy would cancel out with that guy. So now we're getting to a simpler expression here. So now we have NART ln, and I'll go ahead and just re-express them as quotients here. So we'll have ln, well, actually, wait, let me just bring everything down first. So ln PA plus NB RT ln PB minus NART ln P minus NB RT ln P, right? So using this same rule of natural logarithm, right, we notice that we have NART, right, these two terms that are multiplied by NART. So that's going to give us NART ln PA over P, right, plus NB RT natural log of PB over P, right? So really we just get these two terms that all depend on the total pressure, right? And the partial pressure, right? So keep in mind one of the general rules from Dalton's law of partial pressure. If you have this partial pressure over the total pressure P, this is actually going to be the mole fraction for each individual component, right? So we can actually re-express this as NART ln mole fraction of A plus NB RT times the natural log of the mole fraction of B, right? Now what we can actually do here again is just to get everything in terms of the mole fraction. We can divide both sides, or we can multiply everything by 1, and in this case the 1 that I'm going to multiply by is just going to be in total over in total, right? If we do that, then we get everything in terms of the mole fraction. So we'll have in total times the mole fraction of A, RT ln mole fraction of A, plus in total times the mole fraction of B, RT, ln the mole fraction of B, right? So now one thing we know about the mole fraction, right? So I want to kind of get to a grand conclusion here for the delta G of mixing, right? So we've talked about the spontaneity of mixing two gases together. We talked about gases being able to spontaneously expand to fill their volume, and that if they'll mix spontaneously, right? So we can actually get that from this expression for the Gibbs energy of mixing, right? What we see here is that this is always going to depend on the natural log of the mole fraction. Well, the mole fraction, if there's any mixture going on here, right, the mole fraction of A is always going to be less than 1, and the mole fraction of B is always going to be less than 1. If you take the natural log of a number that's less than 1, you're always going to get a negative number. So that means that the delta G of mixing is always less than 0, which means that it's always spontaneous. Right? So by getting down to this expression that depends on the mole fraction of both components, we're able to show explicitly that this Gibbs energy of mixing for ideal gases is always going to be a spontaneous process.